Okay, so in this session, we will introduce the conservation laws that will be used in analysis of fluid flows. So if you remember, in fluids, we mainly work with a very important theorem اللي هو Reynolds transport theorem. هنرجع نتذكر the Reynolds transport theorem, which is used in control volume analysis. And then we will see that using the same theorem, if I just vary the variable of interest, I can have the continuity equation, I can have the momentum equation, I can have the energy equation, and Bernoulli's equation. So from the same theorem, I will derive the main conservation laws of fluid mechanics. So first, let us remember what is the Reynolds transport theorem. What is the idea about this theorem? You consider a certain control volume and a control system. So what is a control system? When I say control system, يعني the mass of it is fixed. يعني I am following a mass and I'm studying its behavior. So the property of a system is that M is fixed. Okay. While for the control volume can have a variable mass. So you can have fluxes in and out of the control volume. And in any fluid analysis, let us consider نحن هنشتغل كتير على pipe systems. Okay? If I have a pipe and I have a flow that is coming in and another that is going out. Okay? Now, if I'm considering the control volume of interest who will pipe, and if I do a boundary like this is the control volume I want to study. Okay? And its control surface is the lateral surface of the tube, periphery of the tube. Okay? So what is happening, because I have fluxes that are coming in and others that are going out, what will happen is that the mass inside my tube is changing. It's not the same particles that I am observing. See new particles that are coming in and particles that are going out. So this is a control volume. Okay. On the other hand, if I want to look at a control system, I should observe if you want, I should look in overall at what is. I can take a mass and follow it. Yani I will give you for the same example. If I take a tube and I am following a certain number of particles that are moving through the tube, شو حيصير؟ في part حتكون بالأول برا التيوب، بس as the time will progress في particles حيفوتوا لجوا، وهيدي البارت اللي كانت جوا التيوب حتطلع لبرا. So if I'm observing the mass, how the mass is moving, هيدا بكون عم بشتغل على control system. And the Reynolds transport theorem will relate both. يعني حيسمح لي أعمل relation between the properties of the fixed mass with properties of the control volume. This is the general rule اللي هي Reynolds transport theorem. And together now we will apply it to have the continuity equation, momentum equation, and energy equation. So to start with, let us do just some interpretation of the terms. The first term هو del by del T of the mass of my system اللي هي fixed, okay, times a property beta of the system. هيدي ال property beta can be variable. فيني اخذ ال velocity, I can take the energy, etc. So depending on beta, if I change beta, the conservation law I obtain will be another one. يعني for example, I can put beta equal to 1. هنشوف سوا if I put beta equal to 1 يطلع لي ال continuity equation اللي هي ال conservation of mass. Okay. بينما if I replace beta, when I replace beta by velocity, يطلع لي momentum equation. When I replace beta by the energy E, I will get the energy equation. So we will see this in detail in this session. Now let us do the analysis of other terms. So this term here, del by del T of integral over the control volume, rho B dV, this one represents the accumulation over time. And if you have a transient process, you might have accumulation within your control volume. هناخد simple example. If I have a reservoir and I am putting water in it, what will happen if my control volume of interest هو الريزرفوار, with time the level of water will increase. ليه؟ لأنه في accumulation of particles in this control volume. So this term will be present in case of transient behavior. يعني مثل ما شفتوا هون, it's a transient problem because with time I am filling my reservoir with water, so the level of water is changing with time. However, when I have a steady application, so if I'm dealing with a piping system and I reach steady conditions, يعني what is coming in, the flow rate that is coming in is equal to the flow rate that is getting out, then this is a steady application. The transient term will cancel out.
دكتور
Yes.
في حدا عم يحكي على الجروب انه اللينك مش ماشي، مش عم يقدر يفوت على الصف.
بس انتوا كلكم مش الحال صح؟
ايه نحن مش الحال.
let me check if we can anyone send the link by WhatsApp? Is it possible for you?
Yes, doctor, working on it.
Okay, please send it by WhatsApp. Okay. So now for the following term here, this is what is happening along the surface of the control volume, because we have defined the control volume as a certain volume which is in interaction with the environment. So we can have fluxes going in and others that are going out. So this term will represent the leaving and entering fluxes to the system. So now, when we apply this theorem in several scenarios, you will see how much it's practical, and it will give us the conservation laws of fluid mechanics. So the first application that is very important here, conservation of mass, okay, for a certain control volume. So what is the idea here, which is called also the continuity equation? So as I told you, all you have to do is to replace beta, which is defined in the Reynolds transport theorem, by 1. If you replace beta by 1, this is what you get. First, you will get del by del T of M, لأنه نحن بالرينولد transport theorem we have del by del T of M times beta of the system. And since beta is 1, we are considering the first case where beta is 1, then I have del by del T of M of the system. But we just defined a system as a system with constant mass. The mass is not varying. So if the mass is fixed, I am looking at a fixed mass. If I derive M with respect to time, it's 0 because it's a constant. So when you apply the Reynolds transport theorem, this one, when you apply it for beta equal to 1, del by del T of the mass of the system is 0 because the system is characterized by a fixed mass. You will only deal with these two terms, okay? And you will replace just beta by 1. So here you will have del by del T integral over the control volume rho dV plus integral over the control surface of rho times VR dot NdA. And let us do the interpretation of these terms. So this term will represent the fluid accumulation or loss. So because rho dV is what is dm, okay? So if I integrate the over the control volume dm, I will obtain the mass of particles within this control volume. And if I have in accumulation or I have a loss, so I have a transient problem, then del by del T of integral over the control volume rho dV will not be 0. But if I have a steady application, this term will cancel out. Okay? So this is to account for fluid accumulation or loss, and as we said, it's characteristic of a transient flow. While the second term, if we look at it, it represents what is the mass fluxes that are crossing the control surface. Because you know how we define a mass flow rate m dot. Who remembers what is the formula for m dot? M dot is a mass flow rate. It's dm by dt. Okay. It can be given by the density of the fluid, rho, times the velocity of the moving flow through the cross section, times the area that we consider. So rho VA represent a mass flow rate, and the unit of it is kilogram per second. So what is happening here when I do VR.NDA, I will obtain this. We'll see how. Okay. So now we will do the analysis of this term. Before moving to the analysis of this term, I will just give you some examples of application for this equation. So let's say if you have a balloon, okay, if you have a balloon and you are doing inflation of the balloon, this means that you are introducing air to it. What will happen is that you have a transient application here where air is accumulating in your system, okay, and your this is a transient application where you have a fluid accumulation, and also you will have a flux that is coming in because air is crossing the control surface of your control volume, which is the balloon. So you will have a moving boundary. So you can have a control volume with moving boundary. It should not. It can be fixed, but in some cases it's not. So this is the case of the balloon. When you introduce air, the volume will increase and your control surface will be moving. And in this case, you have fluid accumulation. So this term, if you apply this equation here, you will simply obtain that what is the accumulation of flow is due to the mass flow rate that is coming inside your balloon. Because here nothing is going outside. So you will just have this term will be restricted to the mass flow rate that is coming inside my balloon. Okay. Another example, if you have a network of pipes, okay, and you have fluxes that are coming in from several pipes and others that are going out. If you are working in steady application, when you reach steady state conditions, this term will cancel out, and you will end up with the following relations, that sum of m dot equals to 0. So you can say that sum of m dot in minus sum of m dot out equals to 0. And we'll use this equation a lot when we deal with pipe networks. Okay. So this is the steady equation in case we have a system, a control volume subjected to different flow rates entering and exiting its control surface. Now let us talk more in detail about this term, which represents the mass flow rate crossing in and out our control surface. Okay, so what this term represents what? Why we put VR.n? What is VR and what is n? So whenever you have a surface, so we will go back always to the same example to understand how we apply the formula. So I'm considering a certain pipe. I have an inlet here. So this is an inlet. And this is my outlet. And now, at this surface, n represent for any surface the normal vector. And the normal vector is always directed, is perpendicular to the surface, directed outward of the control volume. So this is vector n for my inlet. This is n for my inlet. And for my outlet, this will be n. And what is V relative? V relative represents the velocity of the flow minus the velocity of the control volume or control surface. Okay, what do we mean by this? If your tube or pipe is fixed, then the velocity of the control surface is 0, and then your fluid will move relative to it at a velocity v. But imagine that you have a pipe and the pipe is moving at a certain velocity v. Okay, if you bring a jet of water moving at v also, it will not be able to enter the tube because they will move the same distances, so there is no relative motion between them. So if both the control surface and the fluid are moving at same velocity, the fluid will not be able to cross the tube. To cross the tube, I should have the velocity of the fluid larger than the velocity of the control surface. In this case, the relative velocity is what I should consider, because I just care for the difference between the two to know how much fluid is getting inside my tube. Okay, this is why we use V relative and not V of the fluid, because in the example I gave you, if the fluid velocity is equal to the control surface velocity, then the fluid particles will not be able to enter the piping system. Okay, so this is why I should subtract from the velocity of the fluid the velocity of the control surface. In general, in pipe systems, we have fixed systems. This is why for pipes which are fixed, we can just say it's V of the fluid because V of the control surface is 0. But in case we have any application with motion of the control surface, we should pay attention to consider the relative velocity. Okay. So now, why I do when I do Vr dot n, what do I obtain? So let's say this is your area. Okay. If you have an inlet, n as we said is like this, while v is going inward. So for an inlet, when you do Vr dot n, you will get a negative result because it's the dot product of two opposite vectors. So for the inlet, I will get minus v. So v dot n will give me v because n is a unit vector, so the magnitude of it is 1. So it will give me minus v, and then I have minus v times rho times dA. Okay. While for the outlet, I will have opposite sign. For the outlet, n and v are along the same sense. So when I do n dot v, I will get plus v rho dA. Okay, and I will integrate over the area. In case I have constant velocity over the area, okay, so let us consider a certain simplification. If v is constant over the area, what will happen is that I can take them outside of the integral, and I get rho times v times a, which is the expression of m dot. Okay, so this formula is general because it works well with fluxes. It will consider the sign because inlet and outlet fluxes should have opposite signs. And now let us do an application together to see that by applying this general relation, I can compute how the mass will vary in a certain control point. So you deduce the following. Now, if you go back to our equation, our equation is stating what? It's stating that the transient term del by del t, okay, of the mass along my control volume, okay, del by del T of integral over the control volume of rho dV. Now, if I apply this term, we have seen together that this term will give me a negative flux for what is coming in. So it's minus m dot n, and it's plus for what is getting out. So plus m dot out equals to 0. Let us see if this is physical or not, okay? If you take these terms to the other side, what do you deduce? You deduce that this term, which is the accumulation of fluid within my control volume, is equal to the total value of m dot out minus the total value of m dot out plus m dot n, which is very physical, because why I will have accumulation? I will have accumulation when flow rate is coming inside my control volume, and I will have loss, I will use material when a flow rate is going out. So this equation is just telling me that what will be accumulated is the difference between what is coming in minus what is getting out. Okay? Any question on this? Okay. Let us do a small application of the formula. So let us say you have a tank, and it's subjected to flow rates that are coming from two sides, and this will lead, so you have piping systems, let's say, and you are supplying your tank with water, and under the effect of these flow rates, the level of water inside your tank will increase, of course, because you don't have outlets here, you just have inlet. Okay, so if I want to find how the height will vary with time, this is my purpose. Okay, so let us read together the given. The tank in the figure is being filled with water by two one-dimensional inlets. Air is trapped at the top of the tank. The water height is h. Find an expression for the change in water height, dH by dt. Okay, this is what we should do. So here, if you want to apply the continuity equation, first, what is our control volume? It's our tank. Okay, so this is our control volume. Now, what is happening is that I have two inlet fluxes, 1 and 2, and since they gave me V1, V2, I can assume constant velocity over my inlets. So m dot is simply calculated as rho times area times velocity. So if I apply now the continuity equation on this system, what do I get? First, the accumulation term, which is d by dt of integral over the control volume of rho dv. Okay, now since both are inlets, I will use the negative sign, because you remember we said v dot n for an inlet is negative, so it's minus rho 1 a1 v1 and minus rho 2 a2 v2. This should be equal to 0. Now, my purpose is to find the variation of water height in this case. So I will try to express my volume variation function of h. Okay. To do this, what should we do? We should express the volume function of h. Okay. You know that here I am doing integration over the control volume of rho dv. Okay. But since it's water, the density rho is not changing with position. So if I considering my control volume, rho is the same. Rho of water is the same everywhere. So since rho is a constant, I can take it outside of my integral. Okay, and I will divide my volume into two parts. I have in my control volume, I have two fluids. I have water and I have air. So I should consider both cases. Okay. So first, for the water, it's occupying a height h. Okay. So I will divide the total volume into the volume of water plus the volume of air. Okay. Now, for the volume of water, what is the density? It's raw water. So I will integrate first over the control. The integration will be divided into two parts, one for along the volume of water and one along the volume of air. So if you do integral over raw water times dV water, since rho is constant, okay, raw water is not changing along the volume of water, I can take it outside of the integration. So what do I get? I get raw water times integral dV water. Integral dV water is the volume occupied by water. So I can replace this term by, so I get that this is raw water times velocity of water. Sorry, times volume of water. Okay. Now, what is the volume of water? The volume of water is function of the height h of water. It's equal to h times the cross-sectional area of my tank, 18. So now the first term will be here. I will have d by dt. The first term to derive is raw water times the volume of water, which is h, times the cross-sectional area of the tank. Okay. Now plus for the volume of air, what do I have? Same analogy. Okay. I will do the same procedure. Raw air is not varying within the volume. It's varying with respect, if you want, it will vary with, in case here, because you have two fluids, it depends on the fluid. So raw of water is an incompressible fluid, so the density will not vary. And air is compressible, but if I don't have, in some cases, okay, I can treat it as incompressible flow if I don't have high compressibility effects. So here I can add to this plus rho of air times the volume occupied by air, which is AT, times the height of air, which is big H minus small h. Okay. Now, if I want to be very accurate in my solution, it will be a little bit complex for me. Why? Because as I told you, air is compressible. So its density can vary with time, which will complicate the derivative procedure. But how I can go about this, you know, to have a simple solution while still giving me physical results? I can say that the mass of water is much larger than the mass of air. Okay, why? Because of the much higher density of water compared to air. So I can neglect the second term, okay, and just consider the first term, which represents the mass of water. So now if I derive,
دكتور
yes,
على طول نعتبره negligible تبع الاير.
look, in general, air compared to liquid, yes, because look, what is the density of air? It's 1.2, nearly 1.25,
Yes.
while for water it's 1,000. Okay, so it's nearly 1,000 larger.
Okay.
This is why it's fine if we neglect the mass of air compared to mass of water.
يعني ما بيهمنا الفوليوم تبع
هلا اكيد
الهواء.
بيهمنا الفوليوم تبع الاير، بس انتبه هون الفوليوم، يعني تيبلش الاير يكون عنده effect بده يكون الفوليوم تبعه 1,000 times اكثر من الووتر, which is not your case here, صح؟
Okay.
This is why it's here it's a logical assumption to neglect the mass of air compared to the mass of water. Okay,
Thank you, doctor.
okay, so now when we derive this term, rho of water is constant, it's an incompressible fluid, the cross-sectional area is constant, So the only variable is h. This is why when you derive with respect to time, when you do d by dt of raw water times the cross-sectional area of the tank times h, you will take these two terms outside of the integration, which will give you raw water times AT times dH by dt equals to, this will be equal to the summation of m dot n, which are rho 1 A1 V1 plus rho 2 A2 V2. Okay, and in this way we derived the variation of height